So let's talk about something that everybody is familiar with, which is water, right? H2O. You know what this means. This is a molecule, and what I mean by a molecule is it's a free-floating bound arrangement of atoms, one oxygen, two hydrogens, and floats around and bounces around, and it means there's two hydrogen atoms bonded to a single oxygen atom. That's what it means. So in the past, when we have talked about this, what we have basically said is that what this means is that we have two hydrogen atoms, and what this thing means right here is one oxygen atom. That's what it means. But here we have to expand our knowledge of this a little bit further and talk a little, I don't want to say it's different, a different definition, but we need to understand what those subscripts can mean in a different context. So let me talk to you about that. If I write it down again and talk about H2O, I can also say that this subscript, it does mean that in a single molecule there's two hydrogens and one oxygen. That is true. But this H2 can also be interpreted to mean that in one mole of H2O, so let's go ahead and draw a little, I don't know, a little curly brace here. In 1 mole of H2O, there is 2 moles of hydrogen atoms, right? And there is 1 mole of oxygen atoms. Now, most students, when they look at this, they understand this. A single H2O, 2 hydrogens, 1 oxygen. But this can get confusing to a lot of people, so let's talk about it for a second. Here is a single water molecule, right? Let's forget about moles for a second. Let's talk about dozens. Let's say I had 1 dozen of these water molecules, right? A dozen just means 12. So if I multiplied this by 12, I'd have 12 of them floating around. That would be my, in lieu of talking about moles, we'd talk about dozens. So if I had a dozen of these molecules, how many of these red atoms would I have, which are the oxygens? I would have a dozen of them, right? So I would have 1 dozen oxygens. And how many of these hydrogens would I have? I would have 2 of them for every 1 molecule, so I would actually have 2 dozen of these oxygen molecules, H2O, right? So in a dozen of the large arrangement, I would have 1 dozen of these and 2 dozen of the white ones, right? So replace dozens with moles, and that's exactly what you have here. In 1 mole of H2O, which is just a much, much bigger number, 6.02 times 10 to the 23rd molecules, an enormous number of them, there has to be 1 mole of these oxygen atoms, and there has to be 2 moles of these hydrogen atoms in exactly the same way that it works with dozens, okay? So why am I telling you this? Because these subscripts, before we think of just a single molecule and what it means, here I want you to think in terms of moles. If you have a mole of this stuff, then the 2 means 2 moles of hydrogen, and the 1 means 1 mole of oxygen, okay? Why do we care about this? Because this is how we begin to understand the empirical formula of a compound, the empirical formula. So I'm going to read this out loud, and then I'm going to write it down in shorthand form. Okay, we need to talk about something called the mole ratio. Mole means mole. Ratio means ratio. Think about the moles we have here. We have 2 moles of this, and we have 1 mole of this. So when I say the mole ratio in terms of water, all I'm saying is for every 2 moles of hydrogen that we have here, I also have 1 mole of oxygen. So this is a mole ratio between the moles of hydrogen and the moles of oxygen. The mole ratio is what yields the subscripts in the empirical formula, or in the formula, okay? The mole ratio. I want you to wipe away any thoughts of grams. How many grams of oxygen, grams of hydrogen? The subscripts in the formula do not depend on the grams, because in this periodic table, I could slide it over and we could look at it. All of the atoms have different masses. So it's not the masses of the atoms at all that determine the subscripts. It's just how many of the atoms there are. So it can't be the masses in grams that we measure that determine the subscripts. It has to be some counting of the atoms, and that's why the mole ratio is what determines the subscripts there. So when I say mole ratio, I write it as MOL ratio. What I'm trying to tell you here is the mole ratio, it yields the subscripts in the empirical formula. And I'm not going to write this, but on my paper I have parentheses, not grams, because the atoms have different masses. So it's the mole ratio. So let me flip it around for a second. Let's say we did an experiment where you had an unknown substance and you didn't know what it was. But through some measurement, you determined that this substance has a mole ratio such that for every 2 moles of hydrogen that is in this substance, you measure that there is exactly 1 mole of oxygen for every 2 moles of hydrogen. And you're measuring not grams, you're measuring moles, which counts the atoms indirectly because mole is a counting of the atoms. If you measure with an experiment that there are 2 moles of hydrogen for every 1 mole of oxygen, then you can write down the empirical formula, H2O. Because what I'm trying to tie together here is the mole ratio, the ratio of the moles of the elements is what determines the subscripts. And if you zoom in and talk about a single molecule, it also means this. But when you talk about a mole of the molecule, it means this. All right? So that's what the game plan is going to be. When we're trying to determine an empirical formula, meaning we're trying to determine the formula for the unknown substance, what we have to do is measure the moles of each species that's in the unknown substance. And if we can measure, for instance, that there's 5 moles of carbon and also 2 moles of hydrogen and 1 mole of oxygen and 4 moles of chlorine, and we have the moles of everything, then we know the mole ratio of everything. Those numbers are what's going to go into the subscript of whatever the unknown substance is. That's what we call its empirical formula. Now you might say, okay, great, I get that. What is this deal with the molecular formula? How can it be different? Now we have to talk about that briefly, even though we're not going to really work too much with the molecular formula yet. I want you to have in your mind what the difference is and why there is a difference. It's very, very simple. Let's talk about the difference between the empirical and the molecular formula. So the way you write this is empirical versus molecular formula. All right, what is the difference here? Empirical is what you measure. You measure something in the lab and you get some formula. So there must be some difference to talk about what the molecular formula is. Let's talk about what that difference is. So I'm not going to talk about water. Let's talk about another substance. Let's say that you measure C3H4O3. This is what you get, and this is what we call the empirical formula. I'll just put empirical formula. Let's write the word formula. Now, just before you write anything else down, let's talk about this for a second. What does this mean? This means in a lab, somebody hands you a bag of a substance and say, we don't know what it is, figure it out. And then you have some machines in the lab, we'll talk about a little bit more later, experimentally how you do this, but out from the experiments that you do in the lab, you figure out that this substance, what does this mean? This means that for every 3 moles of carbon, there must be 4 moles of hydrogen present and also 3 moles of oxygen present. Now, it also means that you think that it's 3 atoms of this and 4 atoms of this and 3 atoms of this if you zoom into one molecule, right? But we're not talking about that now because in the lab, you never analyze a single molecule. You analyze a bag of it or a giant sample of it, which is usually many, many moles. So the mole ratio, what I tried to tell you here, it yields the subscripts in the empirical formula. This is the empirical formula right here because in the lab I measured that for every 3 moles of carbon there are 4 moles of hydrogen and exactly 3 moles of oxygen. Now notice that we have a whole number ratio there. We're going to come back to the whole number ratio in a second. So that's empirical. We measure that and we write it down. All right, now here's the thing. In the lab I measured the ratio between the carbon, the hydrogen, and the oxygen in terms of moles. And I wrote this down. And in my mind, I think, well, this is the empirical formula. Is that really what the molecule looks like? Remember, a molecule, this is water, so this is not the same molecule, but the molecule is the physical thing that's bouncing around the container. Is this molecule really 3 atoms of carbon bound to 4 atoms of hydrogen, which is also bound to 3 atoms of oxygen? Is it really like that? Well, you're not sure, right? Because all you measured in the lab was the ratio of the elements. But actually, this molecule could be some multiple of these subscripts. So what if you take this molecule here, and let's say you multiply everything times 2. Every subscript times 2, right? So what you would get in that case is you would get C, and then 3 times 2 is 6, and you would get H, 4 times 2 is 8, and then you'll get oxygen, 3 times 2 is 6. So here's a new formula, but it cannot be the empirical formula because the empirical formula comes from measurements in the lab. And what I didn't write down, and I'm going to tell you here out loud, maybe I'll jot it down on the board, the empirical number is the empirical formula is the lowest ratio of moles from the data, the lowest. Think about a fraction. I always come back to math, right? The things people can understand. At least fractions, you should at this point understand, right? If I tell you that you have a fraction 5/10, 5 on the top, 10 on the bottom, 5/10 of a pizza, let's say, 5 slices out of 10, right? Well, you know in your mind that if you have 5 slices out of 10 and all the slices are the same, that's half the pizza. So the fraction 5/10 is the same thing as the fraction 1/2. There are different ways of representing the same thing, right? But in this case, I'm able to multiply by 2 and get larger numbers here. So is the molecule really C3H4O3 or is the molecule C6H8O6? Or maybe I multiply by 3 and I would get C9H12O9. Or do I multiply by 4? Do I multiply by 5? Because you see, in all of those cases, the ratio of C6, 6 moles of carbon to 8 moles of hydrogen to 6 moles of oxygen, the ratio that you get, because these are all even numbers, you could simplify it like a fraction, dividing all of them by 2, and you would get this back again. So what I'm trying to say is that this one, the empirical formula 343, is the lowest ratio of those numbers. Just like a fraction 1/2 is the simplest fraction, right? But the ratio of all these elements is the same in both cases. The ratio of the elements, 6 to 8 to 6, is the same as the ratio of 3 to 4 to 3. I mean, look at it. 3 carbons, 3 moles of carbon, 3 moles of oxygen. 6 moles of carbon, 6 moles of oxygen. It's the same ratio between those two elements in both cases. So the question is, which one's right? Which one really is the molecule? Is the molecule really C3H4O3, or is it C6H8O6, or is it something else? Well, in this case, for this example, this is the actual formula of the actual molecule, and this is called the molecular formula. So the easiest way I know to explain it, and this is called, by the way, ascorbic acid. You're not expected to know that or anything. I just want to tell you, ascorbic acid. All right, so what does this mean? If I had a sample of ascorbic acid somebody gave to me, and I had bionic eyes and I could zoom in on it and see the molecules floating around, what I would really see in there is a molecule, a free-floating structure of 6 atoms of carbon to 8 atoms of hydrogen to 6 atoms of oxygen. And those molecules would be bumping into each other. That's the actual structure of the actual molecule, right? Bound together there, right? That's what we call the molecular formula, because that's the formula of the actual molecule that's bouncing around inside of that thing, right? However, the ratio of those atoms, 6 to 8 to 6, is the same as the ratio 3 to 4 to 3, and the simplest whole number ratio is what we call the empirical formula, right? Now, in the laboratory, when you go backwards and you have an unknown substance, you always figure out what the empirical formula is first, because the machine is just going to tell you the ratio of the atoms. The ratio of whatever the atoms are in the substance, okay? And we're going to talk more about how you do that later, but that's what you get back. But when you get that empirical formula, you write it down, but in the back of your mind, you ask yourself and you just remember that you're not really sure if the actual molecule has that formula. But you know the ratio of the atoms are there, but you're not sure if the actual molecule has that structure or if it's some multiple of that. Just like 1/2 can be expressed as 5/10. But 1/2 can also be expressed as 3/6, or 1/2 can be expressed as 4/8. Okay, so which one of those has actually happened? In the party you went to, did you actually just take half of the pizza, 1 out of 2 pieces? Or did you take 4 out of 8 pieces? Or did you take 5 out of 10 pieces? Or did you take 6 out of 12 pieces? Or did you take 7 out of 14 pieces? Which sequence of events happened, you're not sure, but you know that it all boils down to the same thing, half a pizza. So molecular formula is the actual structure that's floating around. This is the actual molecule, right, here. But the empirical formula is the simplified ratio of that here. And this empirical formula is the lowest whole number ratio. This is what you're going to get from the data. Now, later we'll learn how to find our empirical formula. In this lesson, we'll find the empirical formula. In the future lessons, we will then, from that, figure out what the molecular formula is. And we're just going to multiply by 2. By the way, why are we multiplying by whole numbers? Why multiplying by 2? Why not multiply by 1.5? Why not multiply by 1.8? Well, the reason is because these substances, these are atoms, right? They're discrete quantities. You can't really add half of an atom to a molecule. So most of the time, I can't think of an exception, even though there might be one out there. You're going to multiply the empirical formula by 2 or by 3 or by 4 or something like this to get the molecular formula. All right, last thing I want to say is when we go back to our water molecule, H2O, in this particular case, notice the two hydrogens to 1 oxygen is already simplified lowest ratio. So for this formula, the empirical is equal to the molecular formula. Molecular formula. Right? So H2O, because I can't simplify this any further, this is already the lowest ratio, this is the empirical formula, but we also know that the water molecule really and truly is H2O. We don't want to multiply by 2 or 3 or whatever because we know that the actual molecule really and truly is H2O. So what we need to do now is solve some actual problems. And in these problems, we're not going to be dealing with the molecular formula. That comes later. I just wanted to have it in your mind so you know what the difference is. We're going to be focusing on the empirical formula. So what I'm going to do is give data. We're going to give data to you, and we're going to figure out together what that empirical formula is. Problem number 1 says, for the following compounds, use the values below and determine the empirical formula of each compound. So the first one is 0.01300 moles of carbon, comma, 0.03900 moles of hydrogen, comma, 0.00650 moles of oxygen. So remember, we said that the mole ratio, the ratio of the moles of the different elements that are present, that's what yields the subscripts. And in this problem, we are given how many moles of carbon we have. We are given how many moles of hydrogen we have, and we are given how many moles of oxygen we have. So we already have the moles. All we have to do is find the ratio between them, the lowest ratio, and that one is going to be what we call the empirical formula. So how do you do that? Well, what we're going to do is we're first going to find the subscript for carbon. So for carbon, we are given in the problem statement 0.01300. I'm going to write moles of carbon so you know what it is. We need to divide that by something. Why? Because a ratio is like a fraction. It's like division of two things. And so we need to compare it to something. And what we're going to do is compare it to whatever the smallest amount of the substance, whatever substance is the smallest amount that we have in our problem. So we know we have the moles of carbon, the moles of hydrogen, and the moles of oxygen. Oxygen at 0.0065 is the least number, the smallest amount of stuff that we have. So we're going to divide it by a common number, 0.00650. You always divide it by the smallest amount that you have, moles of oxygen. So you see what we're doing? We're literally taking the moles of carbon and we're dividing by the moles of oxygen, all right? Now remember how fractions work, right? Fractions, any fraction, let's just go over here. The fraction, 2/16. How do you simplify this? Well, you start with 2 and 16. You can divide top and bottom by anything you want to simplify this. So I'm going to divide by 2, but I have to do it to the top and to the bottom. 2 divided by 2 is 1, and 16 divided by 2 is 8. So the fraction 2/16 is the same as the fraction 1/8. What that means is the ratio 2 to 16, 2 apples to 16 oranges, is the same ratio as 1 apple to 8 oranges. Yes, the numbers are different, but the fundamental relationship between the numbers, which is what we call the ratio, that is fixed. When you simplify a fraction, the numbers are different, but the meaning of the relationship between the top and the bottom is what stays the same. So what I have here is a very weird number and another very weird number, but it's still just a fraction. So what I'm going to do is I'm going to divide the top and the bottom number. I'll do it this way the first time, but after this we won't have to do it anymore. I'm going to divide the top and the bottom number, 0.01300, and on the bottom 0.00650. I'm going to divide the top and the bottom by the same number to simplify it. I'm going to divide by 0.00650. 0.00650. Right? Why am I doing that? Because when I divide the top, when I take 0.01300, I guess I'll go down here, and I divide by 0.00650, what do I get on the top? The number 2. On the bottom, I'm dividing by the same thing, so I get the number 1. Now, what was the numerator? It was the moles of carbon divided by the moles of oxygen. So what I've done is I've taken these weird numbers and I've simplified the fraction to something that makes sense. For every 2 moles of carbon, there is exactly 1 mole of oxygen. That is a nice whole number ratio, okay? And so what you can then do, once you have it into this form here, you can just take 2 divided by 1, and then you can just get the number 2. And what we're finding is the subscript for the element carbon. So I'll remind you of that by putting the number 2 there for carbon. Now, this simplifying of the fraction business, I'm doing that just to show you what is happening. Really, all you have to do is divide these numbers together. You'll get the number 2, and then it'll be the mole ratio of carbon. But when I put this here, what I'm really saying is the ratio of carbons that you have compared to one mole of oxygen. So it's the ratio of carbon to oxygen is what it is there. So let's go on to the second one. I think it's going to become a lot more clear. Let's figure out what the mole ratio is for hydrogen. For hydrogen, in the problem statement, I had 0.39000, and that was moles of hydrogen. And on the bottom, it's 0.00650 moles of oxygen. I need to divide each one of these things by the same common number. I'm comparing it to the moles of the smallest number of what I have, which is in this case oxygen. Now the same thing, I could go through the same situation here. I could simplify this fraction and I could divide top and bottom by the same thing, by this, and then I would get a whole number ratio here, and then I would divide them and just get the number. But I'm just going to skip the intermediate step here and just divide these numbers here. So take this and divide by this, and you're going to get well, if you divide top and bottom here, you'll get 6 over 1, which is going to be 6. So if you divide the top by, if you divide the bottom by 0.00650, you get this. If you divide the top by the same number, you get 6. And of course, when you divide them through, you get the number 6, and that's the ratio of hydrogen. So what you're doing is comparing hydrogen to oxygen, and what you're saying is that for every 6 moles of hydrogen is for every 1 mole of oxygen, 6 to 1 here. All right, let's go find the last one here. Let's go find the last one for oxygen. Now for oxygen, the number was 0.00650 moles of oxygen, and we're going to divide that by the same number, 0.00650 moles of oxygen. Now, of course, I could simplify this fraction. What would I get if I divide top by this number and bottom by this number? I'm going to get 1 over 1. And I divide that, and I'm going to get 1, and that's the subscript for the oxygen. Okay, so before we go any further, what do these numbers mean? Because notice what I did is I took the moles of carbon divided by the moles of oxygen, the moles of hydrogen divided by the same thing, the moles of oxygen, and the moles of oxygen divided by the moles of oxygen, which always is going to give you the 1 there. So what I've done when I find this number 2 is I figured out that there are 2 moles of carbon for every 1 mole of oxygen. For this one, there's 6 moles of hydrogen for every 1 mole of oxygen. For this one, there's 1 mole of oxygen for every 1 mole of oxygen. The last one is always the simplest thing. And so what you do is you take this and you put it together, and what you say is the subscript for carbon is 2, the subscript for hydrogen is 6, and the subscript for oxygen is 1. So you get C2H6O01, and this is the empirical formula. Now let's see if this makes sense based on our lesson from before. We looked at the familiar water. We know that H2O consists of 2 moles of hydrogen for every 1 mole of oxygen. Now these numbers I picked to be whole numbers in exactly a 2 to 1 ratio. But I could have picked other numbers that were in a 2 to 1 ratio also. I could have picked, for instance, let's just think for a second, a 2 to 1 ratio, 0.2 compared to 0.1. All you need is one number to be double of the other one. That's a 2 to 1 ratio, okay? I could pick other numbers, but you see, they don't have to be whole numbers. It's just I picked them to make them easy for you to understand here. But in this problem, for every this much of carbon, we have this much of oxygen. It comes out to be an exact whole number ratio. We have exactly double the amount of carbon by moles than we do of oxygen. Moles of hydrogen to oxygen, same thing, except there was 6 times the amount of moles of hydrogen compared to oxygen. And then for oxygen, we just get the number 1. This is the empirical formula. Final thought, remember, the empirical formula is what we get from data. Is this molecule really 2 carbons, 6 hydrogens, and 1 oxygen bound together floating around? Or is it some multiple of that? I don't know. We don't have enough information. But the empirical formula, the lowest whole number ratio, is on the board here. The molecular formula for this could be multiplying each of those subscripts by 2, or by 3, or by 4. It could be a gigantic molecule that would also have the same ratio as what I've written on the board. In the next couple of topics in the future, we'll talk more about the molecular formula. The empirical formula should always be the lowest whole number ratio. All right. Now we have to move on. Even if you don't totally get it here in the beginning, we have to move on because you will get it. It is not a hard topic. We just take each of the moles, find the whole mole ratio, and then those are the subscripts. That's it. Now, the next problem is a little trickier because in this case, we're determining the empirical formula and we're given 11.660 grams of iron, 5.010 grams of oxygen. So you cannot find the empirical formula from the grams. Remember, we said that the mole ratio is what yields the subscripts in an empirical formula because the mole ratio is counting the atoms. The grams, all these atoms have different masses, so you can't do the gram ratio. You cannot just divide these grams and somehow figure out what the formula is. It's not correct. But we know how to convert all of the grams of an element to the number of moles because we know what the molar mass is. So what we have to do in the beginning, before we really do anything else, is we have to convert 11.660 grams of iron. And we have to convert that to moles. Now, if we look at iron on the periodic table, it's 55.85. What is that? Grams per mole. So what I do over here is I say that 1 mole of iron is 55.845, and I'm just using a little more accurate number, grams of iron. So that's grams per mole. And I arranged it this way so that I can cancel grams with grams. So if I take 11.660 and divide by its molar mass, what I get is 0.20879 moles of iron. All right, now we got to do it again because we have another species here in our little experiment. And we're also told that we have 5.010 grams of oxygen. Right, now we've used oxygen and up. We know that 1 mole of oxygen is 15.999, 999 grams of oxygen, right? And we cancel the grams with the grams, so essentially we have to divide again. So if we take 5.010 divided by 15.999, what we get is 0.3131 moles of oxygen. So you see, in the previous problem, we were given how many moles of everything we had, as if a machine just spit it out on the screen and it said, here's how many moles you have. But in reality, we use something in the lab called a mass spectrometer, and it usually gives the relative abundances and the masses of the different elements. So usually the machines give you the masses of what is in there. However, we can convert all the masses to moles because we know the molar mass from the periodic table, right? And so then once we do that, we can calculate how many moles of each thing we had, and now we have to finish up the problem by finding the mole ratio. All right, so we only have 2 species here, and the iron is the smaller number. So what we're going to do for the iron is we're going to say, for the iron, we're going to calculate the iron number first. We're going to say that it's basically 0.20879, that's moles of iron. And we're going to divide it by the same thing because we're dividing everything by the smallest number of moles we have, 20879 moles of iron. So when you divide these numbers together, what do you get? You get the number 1. Okay, so let's move along, and that doesn't really tell us much. It's like the subscript of iron would be 1. Okay, let's move on to the next thing. For oxygen, right? For oxygen, we're told, we calculate, I should say, 0.3131 moles of oxygen, and we're going to compare that or divide by, find the ratio, the moles of the iron, which is 0.20879 moles of iron. So we're figuring out the ratio of the moles of oxygen to the moles of this. Now we could simplify the fraction, divide top and bottom by 0.20879 and by this. And what we're going to get is we're going to get 3/2, which is 1.5. All right, so here's the problem. You were tempted to say, all right, Fe has a subscript of 1, and oxygen has a subscript of 1.5, or the fraction 3/2. So oxygen 1.5. Okay, you cannot write a formula with iron having 1 atom and oxygen having 1.5 atoms. Why? Because you can't have half an atom, okay? So all it means is that when I measured things, I did find the correct ratios, but because they're not whole numbers, I have to multiply, just like you can multiply fractions, because these are just ratios of the amount of moles I measured. As long as I multiply both numbers by the same common factor, then I don't change the ratio between them. So the fact that I had this is, means that I have to multiply each of these subscripts by 2. Each of these ratios need to be multiplied by 2, essentially. So what you can do there is you can say, how do you want to do this? I guess the way you do it is you say iron. The ratio really is going to be 1 times 2, so you get 2. And for oxygen, 1.5. How do you make a whole number out of this? We're going to multiply by 2. Because I know 1.5, which is the same as 3/2, multiplied by 2, I'm going to get 3. And then I use these numbers down here. And so the actual empirical formula, Fe2O3. This is the empirical formula. So I'm going to put empirical formula. This is the empirical formula. Now keep in mind, Fe2O3, it doesn't really mean that that's the actual, well, in this case, it's actually iron and oxygen. So this is an ionic compound. So this is the lowest whole number ratio. This isn't a molecule at all, is what I'm trying to say. I've been drawing the comparison to water, trying to make you understand that there's a difference between the molecular and the empirical formula. But in this case, since it's iron and oxygen, which is an ionic compound, really it's just the formula unit in the lattice that you're calculating, which is always the lowest whole number ratio. So this would be the formula unit, since this is not a molecule at all anyway. The lowest whole number ratio is what you want. So there really is no molecular formula for this because this isn't a molecule, is what I'm trying to say. So Fe2O3, that's the empirical formula. The bottom line is when you do the whole number, the mole ratio, and when you do that division, and if you get numbers that are not whole numbers, then you have to multiply both of them by a common factor to get the smallest whole numbers you can get. These are the smallest whole numbers I can get to satisfy this. All right, making good progress. Let's take a look at problem number 3. Now this one's different because I'm giving you the information about all 3 of the atoms, but I'm giving it to you in a different way. What's the empirical formula when I have a sample that contains 40% carbon by mass, 6.7% hydrogen by mass, and 53.3% oxygen by mass. So when you are given percentages, usually it's going to specify if it's by mass or not, and this is what it means, it's by mass. So what does it mean to have, let's take something simpler. If I told you something was 50% oxygen by mass, then what it would mean is that if I had a 100-gram sample of it, that 50% of it, 50 grams, would be oxygen or whatever element I was talking about. If I had a 1,000-gram sample and 50% by mass was some element, carbon or whatever, then 500 grams would be carbon. So you see, you're given it in percentages, but really we don't want to work with percentages. We ultimately want to work with moles. Since we're given percent mass, what we do is we assume a 100-gram sample in our mind. We assume a 100-gram sample. You don't have to. You can assume a 1,000-gram sample or a 1,000,000-gram sample, but a 100-gram sample is very easy for us to hold in our mind. And then we say that if we have 40.00% by mass of carbon, then in this sample, what it means is this is a 40.00 grams of carbon. In this sample, that would mean 40 grams of carbon, right? And what it would also mean is 6.70% hydrogen by mass would mean 6.70 grams of hydrogen in that sample. And by oxygen, 53.3% by oxygen would mean 53.30 grams of oxygen. So if you add this number to this number to this number, you're going to get 100%, right? Or not 100%, sorry, 100 grams. So if I assume 100 grams, all of the amount of grams of everything should add up, and all I'm doing in my mind is I'm multiplying 40% times this, and this much percent times this, and this percent times this. But when I choose a 100-gram sample, since percentage is always in relation to 100, it's very easy just to come up with the numbers. So I give you percentages. It's very easy to get grams. That's the bottom line. Make your life easy. Assume a 100-gram sample. Now I know the grams of each species involved. Now, can I just do the ratio, the mole ratio with these grams? I can't, because mole ratio is what I need. So I have to convert these to moles. So 40 grams of carbon, right? I know that 1 mole of carbon is 12.011 grams carbon. Cancel, cancel, and then what I get when I take this and I divide by this is 3.330 moles of carbon, all right? Moving on to the next one. I now know that I have 6.70 grams of hydrogen in the sample that I'm talking about, right? And I know that 1 mole of hydrogen is 1.008 grams of hydrogen. Cancel, cancel, right? And so I take the 6.7, I divide by the 1.008, I get 6.65 moles of hydrogen. All right, moving right along, I have 53.30 grams of oxygen. How do I convert that to moles? I know that 1 mole of oxygen is 15.999 grams of oxygen. Cancel, cancel. So whenever I take the 53.30 divided by 15.999, I get 3.331 moles of oxygen. So now I'm at the same place here with moles of each species as I was at the beginning of the first problem, where I just gave you, we were just given the number of moles. So now we do the actual mole ratio. We have to figure out which one of these is smallest, because that's the one we're going to divide by. So 3.331, let me double check myself here. Yes, these are very, very similar, but this is the smallest one here, the carbon right here. So what I'm going to do for the mole ratio is I'm going to start with 3.330. This is for carbon, moles of carbon, and I'm going to divide by the smallest number, which is the same thing, 3.330 moles of carbon, which of course is a 1-to-1 ratio. Divide top and bottom by this number, you get 1-to-1 ratio, which is just 1, and this is the subscript for carbon. Next, we're going to take the hydrogen, 6.65 moles of hydrogen. We have to divide by the same number, 3.330 moles of carbon. Now you have to be a little careful here. You see, when I divide these numbers, when I take this and divide by this, what do I actually get? 1.9969. You see how it's so close to the number 2, then basically you can just round up to the number 2. So I'm going to say this is a ratio of 2, and I'm comparing the hydrogen to the carbon, so this is going to be the subscript for the hydrogen, right? Why am I getting a number that is very, very close to 2 but not exact? It's because there's always experimental error when you do any measurements. When you get a machine that tells you something is 66.70% by mass of hydrogen, how accurate is that? There's always some experimental error. So when you're doing these ratios, when you get a ratio that's very, very, very close to a whole number, just round it up. Now, if you get a ratio down here that's very far away from a whole number, you can't round it up. But if it's very, very close, then you just round it up to the next whole number. All right, finally, we have, for oxygen, we have 3.331 moles of oxygen, and that's compared to 3.330 moles of carbon. That's the smallest one. Now look at this. Same sort of thing. These numbers are almost exactly the same. What do we actually get? 1.0003 with a bunch of decimals after it, which is very, very close to the number 1. It's so close to the number 1, I'm going to say it's experimental error. Basically, it's giving me the number 1 back. So when I put all of this together, the empirical formula is going to be for, and this one was for oxygen, right? For carbon, carbon was the subscript 1, hydrogen was the subscript 2, and oxygen was the subscript 1. So C1H2O1, this is the empirical formula. Now, in the back of your mind, you need to know and be thinking that this is just the smallest whole number ratio of the moles that we have in our sample. So this is what the molecule could look like. It might be 1 atom of carbon and 2 atoms of hydrogen and 1 atom of oxygen. However, it might not be. It might be a whole number. The actual molecule in your container that you measured might actually be exactly 2 times the subscripts of all of those, or exactly 3 times or 4 times. Because if it was times 2, it would be C2H4O2. If it was times 3, it'd be C3H6O3. If the molecule were actually one of those bigger ones, then the mole ratios I would get would be the same, because we're dividing by the number of moles of the other species, so the ratios between them would be the same, even if the molecule were a bigger whole number ratio of this. So this is the empirical formula. The molecule might actually have that shape, but it might be a multiple, a whole number multiple of what we've written on the board. But this is a candidate. It might actually be this. We have a word for that called the empirical formula. All right, we only have one more, and it's pretty simple. Same thing. Here's some information about samples. Using the values, determine empirical formula. And for the next one, it's 0.0630 moles of chlorine atoms and 0.220 moles of oxygen atoms. Notice we're given the moles of the atoms there, so we don't have to do any conversions. We can just directly calculate the mole ratio. All right, so how many moles of chlorine did it say we had? For chlorine, it said we had 0.0630 moles of chlorine. Now, we always want to divide by the smallest amount of moles we have, and the smallest is the chlorine, because for the oxygen, it's much bigger, 0.22. So we don't want to divide by that. We want to divide by the chlorine, 0.0630 moles of chlorine. Of course, this is a ratio of 1 to 1, which is the subscript of 1 for the chlorine. All right, next, we have to write down what the mole ratio is for the oxygen, 0.220 moles of oxygen. We're going to compare that to the moles of chlorine, 0.0630. We're always dividing by the smallest number of moles we have in our problem, right? So what do we get? When we divide these guys out, we get actually something close to 3.5, and this would be the subscript of oxygen, right? However, we can't really have that, because if we did, we would have a chlorine with a subscript of 1 and oxygen with a subscript of 3.5. Now, we can't have that, right? But what we can do is we can multiply each of these subscripts by a common number. And we know, since this is 3.5, the easiest way to make it a whole number is to multiply by 2. So what we can do is multiply the coefficient of this is Cl. The Cl by 2, and then the oxygen, we multiply by 2, and then we get O7. So Cl2O7. And this is the smallest whole number ratio that we can get between these guys, because we can't divide these subscripts by anything to make them smaller and still have a whole number. And so this is the empirical formula. Now, notice that chlorine and oxygen are both on the right-hand side of the periodic table. So this is a molecule. This is a free-floating molecule bouncing around the container. Is the molecule really 2 atoms of chlorine and 7 atoms of oxygen? It might be, or it might be a whole number ratio of that. That would be the molecular formula. If it's times 2, it might be Cl4O14. Or if it's multiplied by 3, it might be Cl6O21, for instance. And you're not sure based on the given data, because all you were given is the amount of moles of each species. That can only give you the empirical formula. Later on, we talk about how to find that molecular formula, but basically you have to have additional information to determine if this is the molecular formula or not. So in this lesson, we have started at the beginning and talked about the most familiar thing, which is water, and we talked about that the subscripts do tell us how many atoms are in each molecule, but they also tell us how many moles, or relative mole ratio here, in 1 mole of the molecule. We learned that the mole ratio tells us the subscripts in the empirical formula, and then we talked about empirical is just the smallest whole number ratio from the data to give us a candidate for the molecular formula, but the molecular formula might be 2 or 3 or 4 times these subscripts, and you just don't know. The empirical formula, though, is the smallest ratio between them. Sometimes the empirical formula and the molecular formula can be the same, because we know water really is H2O, and this is also the lowest whole number ratio. In order to figure out what the empirical formula is, if you're given the moles of the different substances, all you do is you take those numbers and you divide them by the smallest number of moles you have. You're just finding the ratio between them, and hopefully you'll get whole numbers out of it, in which case they go straight into the empirical formula. But if, when you do this division here, in some cases you have to figure out the moles from the molar mass, but when you do the division and if you get numbers that are not whole numbers, then you need to multiply both in order to convert from this to whole numbers. And so when we do additional problems, if you have been given in your problem statement percentages by mass, then you need to assume a 100-gram sample to get the masses, to convert to moles, and then to do the mole ratio. All of that is how to find the empirical formula. I'd like you to solve all of these yourself. Follow me on to part 2. We'll continue practicing solving slightly different kinds of problems to find the empirical formula. Learn anything at mathandscience.com.